Hello, my name is Gokul Vasan. I work as Senior Software Engineer in India. I'm going to present the paper Online Working Set Change Detection with Constant Complexity. We see the algorithm that we are going to present today will act as a cornerstone for memory management algorithms in scalable systems. Let me motivate on what the paper is trying to address. Increase in DRAM capacity has enabled memory-intensive applications like big data and machine learning. However, it has induced other problems like memory pollution. What we mean by memory pollution is retention of cold pages in the memory till the reclamation algorithms are triggered, causes unnecessary power consumption due to memory refresh. Further, the reclamation algorithms are approximated algorithms, meaning it has to run very often to rearrange the pages as per its access rate to determine the accuracy. However, running them very often will also hinder the payload performance. Generally, watermarks trigger the reclamation algorithms in operating system. And these watermarks are basically statically defined and are placed near the memory exhaustion. This causes out of memory panic and unresponsive systems. The goal of this paper is to make the operating system aware of memory access behavior so that we can eliminate all the problems that we mentioned before. This can be made possible by identifying the moments a task shifts to a new locality without any hardware support and no offline preparation. These moments can act as essential intervals to proactively trigger reclamation algorithm, such that only the working set pages are maintained in the main memory and proactively trigger page compaction, reducing the external fragmentation, or adapt certain memory related applications like the application that collects the statistics of the memory to become an event trigger rather than the polling based or fixed interval probing applications. To understand the certain aspects of our proposed algorithm, we will run you through some background from which certain inferences of the algorithm is taken. To begin with, we start with working set model. Basically, if a process is running and we stop at the time t and look back for the interval tau, the number of pages that has been accessed or the pages that has been accessed has a higher probability that it will be accessed again in the immediate future. During the days of scarce memory, the working set as a memory policy dictated the ground rule to avoid thrashing, which says that a program's resident set size is at least the working set size. However, to reason a program's memory at a much higher perspective, the phase transition model helped. At any given point of time, a program's access behavior can be seen to be in one of the two phases, which is transition or in phase. In transition, needed memory for the execution is not available in the memory. So the system falls at a much closer time intervals. While in the holding state, the system stabilizes and starts executing without any page faults for a relatively longer period of time. To understand this, let me explain an hypothetical example that has been given here. So initially the page, as the system initializes, it allocates 4 pages and then loops on these 4 pages that has been allocated and tries to manipulate it. And then when it moves to the next execution step, which we call the transition step, allocates another 3 pages and starts manipulating these 3 pages. So you will notice that during this allocation of 4 pages, there will be a close page faults at a successive page faults in this interval. While during the holding times that it actually stabilizes and starts executing for relatively a longer period of time. Now the bounded locality interval. The memory locality is basically cascaded. This model tries to reason on the cascading of the localities, where the larger prime locality is consisting of a much smaller ones. This prime locality is proved to be more stable and independent from the neighboring prime localities compared to the nested smaller ones. This is a simple example that tries to actually give you how the localities can be nested. This shows that tau in the working set is not a constant value. Lifetime function is basically a method or a function that measures the degree of locality. It is defined as a mean number of page references between the page faults. The function will exhibit a relatively deeper concave curve between its program's transition to the next working set. As an example, you can see here there is a deeper concave curve between the page fault 2 and page fault 4 because there is a larger reference string here compared to the neighboring ones. This can be seen to be a prime locality that is transitioning to the next locality. A key observation to take away from this background is a primary locality shift to another primary locality will have a relatively high single point execution time value between those page faults compared to the other page faults. To make the algorithm work, we define certain set of basic building blocks. The first is the interpage fault virtual time, which is basically the wall clock time difference between two consecutive page faults of a process minus all the preemptions that occurred between them. The following figure below shows one instance of computation between two page faults, how the IPFET is calculated. The local maxima during the locality change. The moments when a program transitions to a new locality, we will notice a relatively high single point IPFET value. These spikes can clearly be seen as outliers. Our transition program runs to identify such outliers. In this example above, when we move from the holding time to the next transition step, when the IPFET is plotted in the y-axis, you can clearly see a spike. Then we model the locality of a program into a DFA, where when the process enters the program, it initializes itself with a set of initialization pages, during which it enters the init state, and then it stabilizes itself in the holding state, and then it transits itself to the transition state when it moves to the next step of execution. And then finally, when it exits the system, it moves to the exit state and then goes out of the system. The transition function detect locality change actually does this transition, and majority of our algorithm will be behind how we define the detect locality change. Detect locality change. This is our transition detection algorithm, and it's an online algorithm. On each page fault, an IPFET is generated by a task. So it's a stream of data. To make the algorithm work, we define three main data structures to manage the data. One is the self-adaptive noise band. Second one is the short-term moving average. Third one is the long-term moving average. All the data are maintained as a normalized average value, hence needing constant space. Also, the computation needed to manage these data structures are simple, non-iterable operations needing constant time. Hence, our overall complexity is O of 1, that is constant complexity. Also, to note here that our computation is insignificant, so it can be adapted to any real-time system or time-sensitive systems. To begin with, let's start understanding how we move to the transition state, which is a simple condition check. When STMA is less than the LTMA and the current state is the holding state, we simply move to the transition state. Similarly, for the holding state, we check a similar condition where the arrived IPFET value is greater than the noise band and the current state is either transition or init. Then we don't immediately define the condition as holding, because we wanted to avoid false positives, because there may be an element in the future IPFET value that is larger than the currently arrived. So to avoid such false conclusion, we declare the current IPFET value that satisfied this condition as a presumptive value, and we memoize it in the VT variable, and then we start the hypothesis test algorithm. Hypothesis test algorithm is a simple conditional checks. On every arrival of IPFET value, the VT that is being memoized is checked for the condition that it is greater than the VT value. If so, we declare the current VT value as noise, and then which is actually taken by the noise band to normalize itself. Else, we wait for the near future. On every IPFET value, this condition is checked. If the near future is reached, then we emit up and then move to the holding state. This reduces the probability of false positives. Finally, the self-adaptive noise band. So clearly, the locality noise is a deviation from the normal behavior. However, it failed to qualify itself as a primary locality element. Addition of only these elements will numerically raise the band and may fail to identify relatively small prime localities. In order to mitigate this challenge, the adaptive noise band algorithm adds itself with some adaptive elements that will normalize the noise band. So basically the noise band is the average of maximum of the elements encountered during the init state, minimum value among the elements that deviated from the noise band during the holding state, maximum value encountered per LTMA length during the transition state, and the elements that fail to qualify as an outlier in the transition state. We did evaluation to understand the following. First is the real world evaluation, where we tested the accuracy of the algorithm on real world applications. Second is the theoretical and baseline evaluation, where we check the effectiveness of our evaluation techniques over the real world evaluation, how accurate we were in the real world application. Second is the accuracy of our algorithm compared to other locality change detection algorithms. Finally, we also did empirical overhead evaluation. The results are transformed into binary classification to bring the evaluation to the same scale. Further, this enabled us to use binary classification formulation for our evaluation. The values that are identified as outliers are represented by a positive value, that is label 1, and others are represented as negative value. An optimal offline algorithm is used to evaluate the real world applications, where an optimal offline algorithm will look into the complete sequence of the data to generate the ground truth, and it uses skew correction as the basis, and values that are eliminated from the data to bring the data to normal distribution is seen as ground truth, against which the online algorithms generated results are compared. Trace-based evaluation method is used to evaluate real-world in-memory data-intensive applications. 4 different databases from 4 different types have been used to get this evaluation working. The presented result is just an overview of the evaluation result. More detailed result can be found in the paper, where the accuracy is around 89%, and F1 score is around 65% and F05 score is around 74%, where the F1 and F05 score represents the harmonic mean between precision and recall, where F1 score represents equal weightage between precision and recall, while the F05 score gives more weightage to the precision, and the overall loss or inaccuracy in the algorithm is just 10%. Our evaluation over 4 different databases with 33 different experiments in total showed us that the algorithm emits no false positives. To get the theoretical evaluation working, we used synthetic trace with marked faces, where oblivious adversary model is used to generate the trace, which means that it generates a complete synthetic trace sequence in advance and is unaware of the behavior of the potential users, which depicts most of the user programs. 2 extreme memory access patterns are used to generate the reference string, namely sequential and random. We notice that this is enough to cover all the intermediate patterns that a program can emit. 52 experiments were run in total over 4 well-known algorithms that is described in this table. We notice that the proposed online and the offline algorithm has a theoretical accuracy of 100% and F05 and F1 score of 98% with 0 loss, which shows that our offline algorithm is a very good method to evaluate any algorithm that actually tries to do phase transition behavior evaluation. The concise representation of the IPFET value allowed our offline algorithm to generate the required result with less than 1% of computation compared to other offline algorithms that used reference string or reuse distance as the measure unit. Finally, we conducted the overhead evaluation with 529,974 page faults, and we saw that we induced a negligible overhead of just 0.506%. We proposed a novel software-based solution for embedding knowledge on programs' memory allocation behavior into operating systems memory management with negligible overhead. Our evaluation on real-world application shows that we have an accuracy of 89% with just 10% loss, and the theoretical accuracy is 100% with zero loss. The implementation of the algorithm as a DFA that detects the essential moments in which a task shifts to a new working set can provide meaningful sporadic trigger events to the operating system's memory management. For instance, we can reformulate the scanning process in the reclamation algorithm to maintain only the working set in the DRAM-based main memory, while other pages can be evicted unsecured in non-volatile memory or storage. We intend to explore many other such applications using this algorithm in the coming future papers. For any further questions or any further debate, please don't hesitate to mail me. Thank you.